Okay, in this video, let's look at how to do the big M method in R. The, the big thing is that R doesn't allow you to sort of have free variables, at least with the kind of linear algebra still working out. It doesn't. R is not an algebraic system. It's numeric, and so it's got to think of numbers. You could probably code this up in Mathematica, which does symbolic manipulations, and you could do the big M using a big M in that system, but it doesn't quite work here. So we got to put in a value for big M, and so we'll choose 1,000 because 1,000 is bigger than any of the coefficients anywhere else in the problem. The kind of good rule of thumb is choose something 10 to 100 times bigger than any of the coefficients in the problem. Okay, so we're going to set big M equals 1,000. Set up four rows, 8 columns. Here's the matrix, putting in negative big M in that top row to begin with. Okay, so if we do that, we're going to get negative 1,000 in both the spots in the top row there. Our initial solution, we're going to set up with an initial basis of Z, SA, SB artificial, so the second constraint artificial variable, and third constraint artificial variable. Okay, because we have these negative big M's in the top row, we need to do half a step like we did on paper, but we have to do that half step right here. And so we're going to essentially form the B matrix, do that pivot step right now. So we're going to form the B matrix from our basis columns. We're going to solve that B matrix with the tableau. And doing that step will transform our tableau, get rid of the negative big M's that were here and here in our basis columns. And so now we've got standard basis vectors in SB artificial variable and SC artificial variable. We've got standard basis vectors. Okay. From then we can read off on the right-hand side. And so our Z value at the beginning is 30,000. Okay, that's the 30M that it was before when we were doing this paper pencil. SA is 4, SB artificial is 20, and SC artificial is 10. Okay, and now the rest of the steps are pretty similar. The main difference is that we're doing a minimization problem. So when we test for our optimality, we want to look for the maximum or most positive cost in this top row. So we see positives here and here, and we'll choose X2 because it's got the most positive value in the objective row. Okay, once we've got that, exiting variable works the exact same way. Still the ratios in the smallest positive ratio that we choose. So the smallest positive ratio looks like it comes from the SB artificial variable. And so that's going to be our exiting variable. And then we're ready to pivot. So go ahead and run this. This code chunk is the exact same as before. We've now got X2 in our basis that's replaced SB artificial. Looking at our resulting tableau, especially paying attention to this top row here, we've got a positive value, and a negative value in that objective row. And so we need to choose one of those positive values for our next pivot. So we're not yet optimal. Our Z value has gone down from 30,000 to 3,353. This ends up being what, 10/3 M plus 20. X2 is 6 2/3. SA is 2 1/3, and SC artificial is 3 1/3. Okay, same steps. We're going to repeat steps 3 and 5 until we get an optimal solution to this problem with artificial variables in it. So scroll back up to 3. Test for optimality. We see that we've got positive values in the objective row. So we're going to choose the largest one to pivot on. So we're going to pivot column for X1. Choose an exiting variable. Smallest positive ratio is going to be SC artificial. And so that's going to be our exiting variable. And now we can go ahead and pivot. Here's our updated tableau and our new solution. If I look at the top row of this new tableau, I'll notice that all the costs are either 0 or negative. And for a minimization problem, I'm all done if the top row is all zeros or negative. Okay, and so this is my optimal solution. Looking at this optimal solution, my objective value is 25. It got smaller from the previous iteration. It's now got no factors of 1,000 in there or no additional penalties in there. It's a little bit harder to tell that here when you replace m with an actual number. But what we can see is we get 5x1 and 5x2. We've got some slack for the first constraint, which is fine. But we'll notice most importantly is that both of our artificial variables are now 0. And if both of our artificial or all of our artificial variables are 0, then we have an actual feasible solution to our initial problem. Okay, so that's optimal. Okay, couple questions or things to think about. What happens if we don't choose big M big enough? So go back to the very top and set m equals 1 and see what happens. So go back up here, set m equals 1, run through until you reach an optimal solution. And I'll pause the recording now, pause the video, do that, and check back in just a second. Okay, what you should have gotten if you set big M to only be 1 is that after only one kind of full iteration through, we get a top row that's all negatives, meaning that we're at an optimal solution, but you'll notice that this artificial variable is still in there, okay? And here's the problem with choosing a big M that's too small is that in essence, it looks like you had no feasible solutions, and that's because if you only give a small penalty, then there's not a lot of incentive to driving your artificial variables to get 0. So if you're going to do kind of the big M method numerically in R, you've got to choose an M that's large enough. That said, a word of caution, avoid using an M that's too large. An M that's too large will cause round-off errors. In the past, I've had some students who put like M is a billion. The problem then is that kind of the way numbers get subtracted and rounding, that's going to cause actual issues there if it's too much bigger than everything else. So a good rule of thumb is about 100 times larger than any other constant, and that should work pretty well for what we're doing here. Okay. Go ahead and try the version. Let's actually do that together. Go back up here. Change M back to 1,000. Big M to 1,000. But now change that second constraint to the one that we know it will run into infeasible solutions. So change that to 36. Okay. Go ahead and run through it again. So run that, run this. I'll maybe point out the one change in code, which I think I didn't emphasize enough before, is that we're finding the largest, and so you change the which min that was here before to which max, and you're looking at the max there. Okay, so ran that, run this, and then pivot. And we get to all negatives here. And so we're at an optimal solution. Our artificial variable is still in there, okay? Later on, when we introduce sensitivity, there's a way to tell whether your big M was big enough, and you can kind of do sensitivity analysis on that. We're not gonna worry about that today, but just choose a big M that's at least 100 times bigger, and you can be pretty confident at the end that if your artificial variables are still in here when you reach an optimal solution, then it means your problem is actually infeasible. Okay, that's it for this video. If you have any questions, don't hesitate to reach out to me, especially if any bits of the code were not making sense.